What I wanted to talk about here is looking at redundancy and inconsistency in a 3x3 system of equations. Now what this means is we're looking at solving a 3x3 system of equations and getting a unique solution for x, y and z, or whatever three variables they use, such that it satisfies all three equations at one single point. However, redundancy and inconsistency both come up when I cannot find a unique solution for these three equations. In that case, there's a couple of possibilities that could occur, and it's one of these two. So I'm going to look at what they both mean and the solutions that come about because of them. Now let's start by thinking about redundancy within a system. Let's imagine I want to consider this system of equations here and look at solving them. So if I set up my augmented matrix, I've got 1, 2, 2, 11, 1, negative 1, 3 and 8, and then 4, negative 1, 11 and 35. If I start to solve this, what I do is I do row 2, take away row 1, to eliminate this value here, and I then do row 3, take away 4 of row 1, looking to eliminate this value here. If I were to do that, I'd get a system of equations that look like 1, 2, 2, 11. My second row would then become 0. Negative 1 take away 2, so minus 3. 3 take away 2 is 1. And 8 take away 11 is negative 3. I've then got my third line, which is 0. Negative 1 take away 8, so I've got negative 9. I've then got 11 take away 8, which is 3. I've then got 35 take away 4 of those, so 35 take away 44, which gives me negative 9. If I were to then do row 3, take away 3 of row 2, with the aim of eliminating this variable here, what that would then give me is a system that has the augmented matrix of 1, 2, 2, and then 11, 0, negative 3, 1, negative 3, and then a bottom row of 0, 0, 0, 0. So I've got an entire row of zeros within this system. Now this tells me that the equation is redundant. So what that means is I've not got one single unique solution that satisfies them all. However, because the row is entirely zeros, I've got an infinite number of solutions that will satisfy it. So what that means is if I say let z equal z, so any value of z that we can choose within our system, what I can do is take row 2, so this one here, and plug that in and play about with it, and I'll end up getting that y is equal to z plus 3 over 3. And if I then do the same with the z and the y here, so take this top row and write it as x plus 2y plus 2z equals 11, shift it all across, now x equals 11 minus 2y minus 2z. If I then plug in the values here for z and for y, what that means is that I'll get x is equal to 27 minus 8z over 3. Now what that means is the general solution for this system can be given is x equals 27 minus 8z over 3, y equals z plus 3 over 3, and z is equal to z. Now what this gives me is a solution which is represented by a line in three-dimensional space, which if I were to allow these to represent three planes, would be a line of intersection between all three planes within our system. And if I were to choose any value of z, that would give me a value for x and y, and if I then continued to choose value of z to be any value anywhere within the infinite amount of values that I could choose for it, I would then continually get a line that follows this equation, and that's where all three of these equations, which if we represented them as planes, would intersect. So I don't get a unique solution, I get an infinite number of solutions in this case. That's what it means when it's a redundant system of equations, that we are unable to find a single unique solution, but instead find a whole set of solution, an infinite number which is dependent upon which value of z we choose, and that has an infinite number of possibilities for the value of z. Let's consider what inconsistency means now. Let's imagine I've got this system of equations here. Now, let's look at solving them. Put it in an augmented matrix and then do our elementary row operations to whittle it down. So if I were to do that, put it into an augmented matrix, I'd get 1, 2, 2, 11. I'd get 2, -1, 1 and 8. And I'd have 3, 1, 3 and 18. Let's imagine I then start to do my row operations. So let's imagine I do row 2, take away 2 of row 1. And I do row 3, take away 3 of row 1. What that'll do is that'll transform my matrix, because remember I'm trying to get rid of these values here first. Top row would stay the same, 1, 2, 2 and 11. Second row would become 0, -5. This would then be 2 take away 4, -3, and then 8 take away 22, -14. I'd then have this value here disappearing. I'd then have 0 take away 6, so I get -5. 3 take away 6, which gives me -3. And then 18 take away 33, which gives me -15. What I'd then do is I'd say, right, so what I'm going to do now is in order to eliminate this value here in row 3, I'm just going to do row 3 take away row 2. So if I were to do row 3 take away row 2, what that would then mean is I get 1, 2, 2, 11, 0, -5, -3, -14. I then have 0, -5 minus -5 would become -5 plus 5, which is 0, -3 minus -3, same logic, that would become 0, and then -15 minus -14 would be -1. So I've now got a matrix that looks like that. One point actually to note is that I could have flipped all the signs here in this row and made it 5, 3 and 15 and then added the 2 rows to eliminate them. The only difference that would then make is instead of -1 is this final value I'd have 1. But both would state the exact same thing. They would be inconsistent. This version here tells me that 0 is equal to -1. If I'd flipped the signs first and added them, I would get 0 is equal to 1. Now that doesn't work. That would break mathematics. You can't have 0 equal to -1 or 0 equal to 1. So this means that the system of equations is inconsistent. There's no solutions at all for this system of equations, whether it's a single unique solution or an infinite number of solutions like we would have with a redundant system of equations. There's absolutely no solution that satisfies all 3 of these equations. So if we were to let this be represented by a set of planes, this would be one of the set of planes where, for example, they would meet in this fashion here. So intersection of 2 planes at a time, but there's no point where all 3 planes would intersect, or no line where all 3 planes would intersect. So there's no unique solution or set of solutions to solve them all. When we're working with redundant and inconsistent matrices, it represents one of these 2 sets of answers. There's either an infinite number of answers, so representing a line in 3-dimensional space, or there's no solution whatsoever. And if we were to look at representing them as planes, this is how it would become. This is exactly the kind of solution that we would get, and we could interpret it in that manner.